Hello and welcome to Toddcast number 33. This kind of starts into what is traditionally considered the start of OChem reactivity. And so because we are transitioning more from review and applications of things you've seen before to, well, new content, I want to emphasize just how I'm going to change my approach to these lectures. And so for anybody who's just starting into these, you skip the first review section. This is your first content-based one. My name is Todd Bennett. I've taught organic chemistry since 1989. Originally started teaching at UC Irvine, been at a few different places, had a company, written a book, have a resume that says I've done this for a long time. And hopefully I can offer some really unique insights for how to look at the material. But no matter how many insights and techniques and tricks and strategies you may have, you still have to know the definitions. And so the first of each of the Toddcasts associated with new topic, we primarily based on definitions and make sure we can apply the information. And then we'll build up gradually. We scaffold it all the way up until we get to more complicated um, questions and bio applications. But for this Toddcast, it's going to be all about doing definitions and just the initial steps into what the topic is. And so I want to start with why they call it what they call it. So it's called a substitution reaction. And specifically, it's a nucleophilic substitution reaction. And we're going to refer to that as SN, substitution nucleophilic, 1 or 2. And that's simply based on the two possible mechanisms, two possible pathways the reaction takes. But the simplest scenario is just a substitution reaction in general. If you've ever taken part in a sport, one person substitutes in for another person. One person goes into the game, one person comes out of the game. And so that's essentially what's going on here. One nucleophile is substituting into the molecule, and a leaving group is substituting out of the molecule. So it's a substitution reaction. So in the simplest case, I have a CN group going in. Notice as a negative charge. And generally speaking, I want to emphasize that a negative will find a positive in chemistry, and that's just how it works. And so the carbon in the middle right here, because it is bonded to a highly electronegative atom, will have a delta plus because of delta minus on chlorine. And so minus is attracted to plus. Typically, we draw the negative coming towards the positive. In reality, the molecules are both tumbling around, and it could be the two come together whatever way it happens. But we bookkeep by having the negative come into the positive, and then this pushing electrons out that way. We'll get through into the mechanisms as we go, but for now, say, why I'm identifying that as a so-called nucleophile, the group going in, and then chlorine, the leaving group, the group coming off. So usually you do a negative for a negative, occasionally a neutral for a negative, and in some instances, negative for neutral, but you substitute one group for another. So CN is going in, and Cl is coming off. So you're substituting a cyano group for a chlorine. Okay, so the CN group is substituted for the Cl. The CN is known as the nucleophile when going in, and the chlorine, in this case, the Cl, is the leaving group. So by definition, the nucleophile is the participant that donates electrons. So the name kind of hints at it. Phile meaning loving, nucleo meaning nucleus or the positive region of an atom. So nucleophile is something that will go for the positive or electron poor, partially positive part of the molecule. So note that it's the partially positive carbon right here that it is attacking. Okay, so a lone pair on carbon will come in and attack that carbon. Okay, the molecule that's being attacked, so right here, loves the electron coming in, so it is an electrophile. And then the group being substituted for is mentioned right here, referred to as a leaving group. So three parts. Nucleophile attacks a nucleophile, and in doing so, knocks off a leaving group, part of the electrophile that falls off. We'll again go into details of the mechanism, but the basic gist, this negative, this lone pair on carbon, is going to come in and attack a delta plus, and these electrons in that bond are going to go up to that chlorine. Okay, so we have our basic premise of the reaction. Okay, so where do we go from here? Well, we're going to look at qualities of nucleophiles, quality of a leaving group, and then ultimately qualities of an electrophiles. But starting with nucleophiles, again, a nucleophile donates an electron pair. Um, you learned that a base also donates electron pair, and in fact, to be a nucleophile, you must be a Lewis base. And just a quick reminder, good way to recall, Lewis base. You need two E's to be a Lewis base. So Lewis base is also a nucleophile, and donate it, or a Lewis base. They're one and the same. Okay, so you would think then that the better the base, the better the nucleophile, but it's not quite that simple. There's two factors that come into play that we have to consider. The size of the nucleophile, in general, the bigger it is, the harder it is to fit into a space. And that's not necessarily impactful on a base, but it's highly impactful on a nucleophile, the size of it. And then the possibility of other reactions. If it's too strong of a base, it can deprotonate a proton. So a good nucleophile sometimes is basic enough to attack, has a negative charge to share, but not so basic that it actually will deprotonate hydrogen. So we always have to consider what's going on. So if it's too basic, again, it's going to remove an acidic proton, and that would make it a base. If it's not able to pull the proton off, 12H plus, then it can attack a carbon with a delta plus. So we can kind of look at it this way. If I'm going to decide whether it's going to deprotonate an H or attack a partially positive carbon, I need to decide how strong it is. So deprotonation is the easier thing to do. It's a lighter atom. You can pick up an H. It's much easier to pick up a tiny little H and has gone with it than it is to actually push your way onto a carbon and create a whole series of formed and broken bonds, at the very least two. So strong bases will deprotonate. So if you add something like a ethoxy, hydroxide, there's a probability, and a good probability depending on the compound, that it will deprotonate it. If there are no H's to deprotonate, let's say it's just CH3, a methyl group with a leaving group, like a chlorine, then there's not really a chance for it to deprotonate it from carbon. So that one probably will be a nucleophile. But in a lot of instances, if there's a proton that be taken off, the nucleophile will act like a base more than it acts like a nucleophile. So if it's a really strong base and there's acidic proton around, it's a terrible nucleophile. It's a poor nucleophile. A weak base won't engage in deprotonation, which actually makes it a little bit better nucleophile. So it's not 100% true. So this statement here is a good general rule, but as always, there's exceptions. And then also size, as mentioned, comes into play. But this is a general rule. And then if it's inert, if it's too weak, just doesn't react, then there's no reaction. It's not a good nucleophile at all. So we'll just say it's a terrible nucleophile. So it has at least have some basic properties. So in general, a good nucleophile must be basic, but not so basic that it starts stealing H's. So carbon with a negative might actually be a better base and not a very good nucleophile because its propensity to deprotonate will be so strong. So let's look at this a little more carefully. So electrophiles, just like the basicity parallels to some extent the nucleophilicity, acidity, Lewis acidity is going to be your guiding light for electrophile strength. So electrophile must have a leaving group, has to have something that can come off, and it must have either a fully or partially positive carbon so that it can get attacked. Electrophile carbon is host to exchange of the nucleophile for leaving group, so that's just to define what that is a carbon that has a leaving group. Okay, so good thing to recognize, acid halides are some of your more common electrophiles because halogens have a high electronegativity or certainly higher than carbon. So they will take on a partial negative, leaving a partial positive on carbon. Also, as mentioned, size plays a role. Two small things can get in and interact and react very easily. Two very large things, not so much. So we often worry about primary, secondary, and tertiary. So primary means the halogen is on a carbon that only is bonded to one other carbon, sometimes known as a terminal uh, position. So carbon number one, R represents a long chain. So perfect example, let's just say I do 1, 2, 3 carbons, so propyl chloride, and more importantly, N propyl chloride or 1 propyl chloride. Okay, secondary, the X is bonded to a carbon that has two R groups. So R and R prime, again, represent alkyl chains. So maybe this is CH3, this is like a CH2, CH3. Maybe this is 9 carbons, this is 14 carbons. The point is, this carbon that has a halogen, X, has two other carbons attached. So a good example, cyclohexane with a halogen on it, in this case iodine. So secondary in nature. And then tertiary, if you follow the trend, it's just a carbon with 3 other carbons attached. So in this case, might be dimethyl, let's say, I don't know, dimethyl propyl chloride. So I have to specify where the methyls are, but let's say this is propyl chain and I have 2 methyls on there, and then the X sticking off. I guess I should IUPAC name. Let's say this is on carbon number 2. So if this was a methyl, this is that, let's say propyl, to be 5 carbons, so 2 chloro, but also 2 methyl. So 2 methyl, 2 chloro on the chain. Let's look at a specific one. So in this case, the longest chain is 1, 2, 3. So 2 methyl, 2 bromo, and I should say it in reverse order because alphabetical, 2 bromo, 2 methyl, propane, also known as T-butyl bromide. T-butyl bromide is going to be the common name we use more often. Okay, the point being, attached to 1 carbon, 2 carbons, 3 carbons, not very crowded at all, a little bit on the crowded side, highly crowded. And so that's going to impact how the reaction goes and how the electrophile will behave and how the nucleophile will interact with it. Okay, so time to rank the nucleophiles based not on size, but on their ability to attack, which will be their ability to share electron pair. Now, in general, I do want to emphasize this. We're going to do generic nucleophiles, but and I'm ignoring the size for the time being, but as they get bigger and bigger, the nucleophilicity gets worse and worse. So things like T-butoxide is one of the compounds. We're going to use that in the future as a very strong base to carry out reactions. It's too bulky and too strong of a base to be a very good nucleophile, but bulky and basic. We're going to use amides and with a negative charge in 2 large groups. The one we're going to use is something, we'll have 2 isopropyls on it, and that's going to be our strong bulky base. And anytime I have a carbon with a minus, so butyl lithium is going to be one of the compounds we use. So if you have an deprotonated alkyl group, hard to make, highly unstable, highly reactive, highly basic. So again, going to ignore the really strong bases, the ones that are just too strong and deprotonate. They're not going to make very good nucleophiles. But as I start going down in size, first off, sulfur within our group, even though the R may seem bulky, S is not as basic as O minus, N minus, or carbon minus. So it ends up, it's not such a strong base to deprotonate, so it's a weak enough base and ends up defaulting into being a nucleophile. Ammonia, weak base, really good nucleophile. Cyano group, very good nucleophile. C5HO, or C6H5O phenoxide, good nucleophile. It's a little bit on the bulky side, so I'm still going to list it there. And a key thing, it's not such a strong base that it deprotonates. That negative charge will resonate into the benzene ring. Therefore, it isn't going to donate it as much as like this alkoxy up here. So it ends up being a good base, a weaker base and a good nucleophile. Okay, they are in the weak base category. Okay, nucleophiles, your bigger halogens, nitrate, the common theme here, HCl is a strong acid, HBr is a strong acid, and HNO3 nitric acid is a strong acid. The conjugate base of a strong acid is weak, and I'm going to say, I guess, significantly weak, which means it is happy as a negative charge on chlorine, bromine, or nitrate, so it doesn't really want to donate in. So they're okay not kind of poor nucleophiles. Um, this last little bit about size, just again, want to emphasize it. The size, the bigger it is, the harder it is to migrate through a solvent and get into a tight space. Um, so it will impact it. So the bigger these R groups, the worse the nucleophile. For now, just want to know the general classes. So I'm going to say these three should be on my list to memorize. Phenoxide, since it's a little bit on the bulky side, won't be as good, so we typically don't list it as our preferred nucleophiles. It still can be. Generally speaking, smaller, easier to attack. Okay, so what are the best nucleophiles then? Should be small, not so basic that they run the risk of deprotonating, and good enough bases, strong enough weak bases that they share their electron density. So, amines, excellent nucleophiles. I put one R that's just enough to donate in and make the N richer, but not so many that it gets crowded. Phosphines, pH 3, again, as the number of H is turned into R groups, alkyl groups, it gets worse. CN minus is one of the very best nucleophiles of all. A deprotonated alkyne. So if you recall, alkynes are stronger acids than alkenes and alkanes, which means their conjugate's a little bit weaker base, so it doesn't deprotonate an H as readily. So these are very good nucleophiles, and they're linear in nature. Triple bond is 180 degrees, so because it's linear, it can spear its way into carbon. So they're actually, no matter how bulky the R is, this part of it is linear and small enough that it can be a very good nucleophile. Then SH. So just like this was good, if it's an H instead of an R, even better. So these are the 5, and again, know these as general groups. So the R may vary, the R may vary, the H could be an R. They'll still be good nucleophiles, but generically speaking, those are good. So let's just look at a typical reaction with it. Pretty much every textbook you'll find will have an example of list of how reactive these compounds are. And so in general, we typically like to compare them to one another as they react with something very similar. And so if they react with methyl iodide, iodide's a very good leaving group. So you can correlate the strength of the reaction, the speed of the reaction, favorability of the reaction with the strength of the nucleophile. So the electrophile is highly reactive. So if the reaction goes instantaneously, it's a great nucleophile. And then as you go down, it gets worse and worse. So notice we had HS minus on the previous page. Now I'm having RS minus. Same, I'm going to put them in pretty much the same category. Phosphines, I had pH 3. Here's R3P. Again, excellent nucleophile. So it's generically listed. Iodine, good nucleophile, but also a good leaving group. So it's kind of, we don't use it that much. Cyanide, excellent. The deprotonated alkyne, excellent. And the amine. So you'll notice the 5 I had listed on the previous page are here. I've omitted iodine because it's also a good leaving group, so it can go on and come off both. And so it may not ultimately form the best product. Okay. Hydroxides, if they're small, alkoxides, if the R is small, can be good. If this R gets too bulky, then this one falls off the list. Bromide, again, like iodide, generally it's a good nucleophile, but it's also a decent leaving group, so it's not one you'll see all that often, at least in the questions you're going to run into if I write them. Then we're back down to the azide, ammonia. Ammonia is a pretty good one. It can get protonated. That's the one problem with it, that sometimes it's not as good. And then as we go down our list, eventually you reach a point where carboxylates are stabilized by resonance, so it doesn't want to share its negative charge as much. Fluoride, highly electronegative, so it holds on to negative, so not that much. So you start getting, I mean, they go from good to bad. But you have this kind of dividing line. Dividing line is arbitrary. I'm going based on a set of notes that were inspiration for doing this class that had it here, but you might see a textbook that defines the dividing line up here, maybe down here. It'll vary. The other factor is the size of the electrophile. With a small electrophile, it's fine. As the electrophile gets bigger and bigger, this list will fluctuate. And solvent. As I change the solvent, some of these might get hindered more than the others. And so this, again, is a general list, not to be memorized, but know the usual suspects and recognize certain things as good nucleophiles. So here's how you'll have to apply it. For each pair, decide which is going to be more reactive. So we have methyl iodide like we had before with this. So there is some memorization in organic chemistry. It's just going to be that. Both N3 minus and Cm minus have a negative charge. So they both, in theory, should be good at sharing electron density. They both, in fact, are good nucleophiles. But if you know your five, your amine, your alkylamine, your phosphine, cyano, deprotonated alkyne, and your thiols, or your deprotonated thiols, are just your best nucleophiles. So in this case, CN minus, that's your winner. So this is rote memorization. So Cl, it's I guess some will call it good, some will call it bad. It's like right on that cusp. Whereas RS minus is like the HS minus, that's your better option. Bromide versus phosphine. So again, I memorized this as pH3. I need to be open-minded enough to say it could be H3P, it could be R3P, it could be 1H and 2Rs, 2Rs and 1H. Again, size hinders it, but bromide just isn't quite as good as the phosphine. OH minus, I think of it as a base, so it could deprotonate. That is one problem I'll run into. But this is one where I don't know what to pick because I don't see either any of them on the list. So I'm going to say smaller negative is probably better than bigger and neutral. So this one, I need my list. I need to take an educated guess. You'd have to have some other fact. I went with the small and negatively charged probably beats neutral and bigger. And I'm going to be right sometimes. It's going to be wrong every now and then. And then ammonia versus the alkyde. The deprotonated alkyne, pretty much your winner in most things. So it can spear its way in. And this one gets hindered by being protonated too often. Pure memorization. So basically, you just play the game. Which one is more basic? Up to a threshold to where it was too basic. And generally, basicity, higher basicity and smaller size will be your better nucleophile. Okay, we played the memorization game. We've applied it. Now I want to also consider leaving groups. So we mentioned nucleophilicity matters. The best leaving group comes from a basic idea of just, I guess it's probably more a psychology, sociology idea. I don't know what science or what class would teach it, but the way somebody behaves in one situation is generally a pretty good predictor of how they'll behave in other situations. I'm a sports fan, so I always think of certain athletes that when they come to a new city, they sign a contract in the new city, they're all happy and elated and say all the right things. But if they're disgruntled where they came from, they're going to eventually be disgruntled where you're at. And you can see this recurring over and over and over. Somebody who is disgruntled at their job will continue to be disgruntled at their job no matter where they're at. Behavior predicts behavior. If somebody has fidelity challenges in early things, they're going to have fidelity challenges. If somebody's loyal, they're going to keep on being loyal. I mean, behavior is predictable. So chemistry, same story. We compare it to acidity. If this X is good at leaving from H, then the correlation, the assumption is it's going to be good at leaving from carbon. So if you leave H very readily, you're probably going to leave carbon very readily. So the best leaving groups are typically the conjugate bases of strong acids. So if you're the conjugate base of a strong acid, you leave H readily, then you're going to be good at leaving from carbon. This is why you'll see most chemistry textbooks, most organic chemistry classes will make you look at the pKa of the conjugate acid of the leaving group. So if I wanted to consider F minus and Cl minus as my leaving group. So which leaving group's better? Well, HF, weak acid, HCl, strong acid. So Cl is better at leaving from H. So this is your better leaving group. There's a correlation. Behavior predicts behavior. So if it's good at leaving from H, if it's a good acid, it's going to be a good at leaving from carbon, it's going to be a good leaving group. Okay, pretty straightforward technique, pretty perceptive. And so if you look at relative acidity, HI is stronger than HBr, which is stronger than HCl. Sulfuric acid is up here, but this isn't sulfuric acid. This has a little bit of resonance into a ring system, so I can't compare that directly. Hydronium, if you add HCl to hydronium, you'll protonate the water, so HCl must be stronger than hydronium, so that's why water leaving group is a little bit worse. Fluoride is down here, weak acid, all the way down to water, is terrible at acidity and basicity. It's just a neutral compound, so OH is a bad leaving group off of carbon. You need to protonate it and make it water. So we're going to learn there's certain groups that are predictable in terms of being leaving groups. And then if you have an OH, you protonate it, you can turn it into a good leaving group. So just as I said, there's about 5 to memorize that you'll see frequently enough for nucleophiles. I'm going to dare say those 5 are going to be the 5 that will be recurring in OChem. Now there's other leaving groups and there's other nucleophiles in the ones in those 2 groups of 5. But if you're carrying out a reaction, no need to make it harder on yourself, both on paper and in lab. So if you want to carry out some synthesis, make some compound, you typically want to start with the easiest, most favorable reactions to get the best results. So know your usual suspects and you'll be good. Okay, we've done the introduction, nucleophile, electrophile, and leaving group. We've considered the best nucleophiles, considered the best leaving groups, and I've said it so ambiguously that there's a general trend, but nothing is set in stone. So hopefully this was a good first step in, and I will see you at the next Toddcast. Bye.